All right, guys, I know you're excited about this section. I know you read it. And there's some crazy birds outside my office. No. We're talking about volumes, and we're going to get this idea that we're going to see perpetuate through Calc 2, this idea of finding a small slice of something and then extending that out to infinity, basically, on a finite interval. So we're going to look at volumes by slicing. You really just need to focus on the disk method and the washer method. There are ways to find volumes with using general areas, but just for time's sake, we're just going to do disks and washers and see how to do this. So volumes by slicing. So find the volume of the solid obtained. This is our first examples. By rotating about the x-axis, the region under the graph of y equals root x, and that region we're just going to look at from 0 to 1. Okay, and so I want you to sketch the region. I want to sketch the region, and I want to sketch a representative disk. So we know square root of x looks like this, right? So let's look at it maybe under, a little bit more magnified, let's say. So I know I'm just going from 0 to 1, right? So I know that the square root of 1 is 1, and it's not super curvy. So that is, sorry, that's a little shaky. Wow, that's really shaky. I don't know why it's so shaky. I probably need to do it faster. There's my curve. So this is the area right here. This is the area that I am going to be rotating. And if you think if I could bring that area outside of the computer screen and come back around, you can kind of see that it would make a solid form, right? So it'd be kind of like a vase on its side that doesn't have a hole in it. A solid vase that will be of no use because you can't put any water or flowers in it, but whatever. So we're rotating about the x-axis. This is going to be different if we were rotating about the y-axis, but we're rotating about the x-axis, right? So if I rotate that, that's going to give me a little, this point 1, 1 is going to come down here to 1, negative 1, and I could think about this rotation, and it'll give me this kind of three-dimensional looking object right here. I hope you can kind of see that. Absolutely look in your book for good examples of drawings of this, or just YouTube some examples. Mine are not going to be perfect, but the whole idea of the disk method, right, was if I just took some x value and I took a slice of it, I would get a disk. And the idea is we want to add up all of these disks from 0 to 1, right? And we kind of talked about the disk. It's kind of like a cylinder on its side with an area times a height, but remember that height is described by the dx. So if I did actually take a slice of this, do you see how it would kind of be a cylindrical looking thing, right? But again, if I shove enough of those in there between 0 and 1, an infinite number of them, those widths really become negligible, and we just call that width of those dx. That's the whole idea on finding volume with disks. So you looked at the formula. That really what I want to think about is I want to think about just taking the area, of this guy right here, right? Just the area of, oh, look at that. It made that beautiful circle. Thank you, whiteboard. So I want to take the area of that circle basically right there and add up an infinite number of them from 0 to 1. And so how do we add up an infinite number of them? We integrated, people. We learned that with the definite integral. That was kind of the main idea of the definite integral when we talked about area. So the area of a circle I know is pi r squared. In this case, I have pi. What is my r? Well, my radius is this blue line right here. So what is that radius? How do I know that distance? Well, you guys, it's sitting on my function y equals the square root of x. So this is going to be the square root of x quantity squared dx. That's where that formula comes from. Just comes from the formula for the area of a circle. And I'm adding up an infinite number of those areas, which will give me a volume. I know that's weird to think about, but that's obviously just pi times x. The antiderivative of x is 1/2 x squared, evaluated from 0 to 1. So it looks like we get pi over 2 as the area of this solid. Okay, I don't know the units on it. I don't really care. If we could give you units, you could put this on an axis that has each unit is a foot or a meter if you would prefer. I don't really care what the units are, but I know they'd be like meters or feet squared. Let's do another one. All right, so let's talk about now about going in the y direction. So let's find, wow, sorry about that. Let me get that back. That was a little bit crazy. That was kind of fun though. All right, so let's look about the y-axis. So let's find the volume of the solid. So I'm gonna go ahead and just say that that's all my examples. Find the volume of the solid obtained by rotating the region bounded by. So I'm lazy, I'm a mathematician. We can be lazy. That's why we find shortcuts for things. Bounded by y equals x cubed, y equals 8, and x equals 0. And I wanna rotate this about the y-axis, okay? So here's a little hint. This is not going to be true in 6.4. So in 6.3, when we're dealing with discs and washers, whatever axis you rotate about, or whatever axis, whatever it's parallel to, the y or the x, that's what you're going to integrate with respect to. So you saw in our first example, right, whoa, I don't know where that came from. Oh, well, that's all right. I don't know why I did that, but let's just put x equals 0. In our last example, we rotated about the x-axis, so we integrate with respect to x. This example, we're rotating about the y-axis, so we are going to integrate with respect to y, okay? So I'm going to do a quick little sketch of this. I'm going to be a little lazy and do this all freehand, sorry, and not use my little ruler, but y equals x cubed, so y equals x cubed, we're here. And I know I'm bounded by y equals 8, 2, 3, 4, 5, 6, 7, 8. And so here's what I have. I have from 0, I have 1 cubed is 1, and then 2 cubed is 8. So that's going to be kind of my curve, right? What else am I bounded by? I'm bounded by y equals 8, which is just a horizontal line. And I'm bounded by x equals 0. And x equals 0, right, is just the y-axis. So this is the area that I'm going to take, and I'm rotating it about the y-axis here, okay? So you can kind of see what this is going to give us. Let me get rid of some of that stuff there. All right, so what are we going to get? We're going to get another kind of bowl-looking thing. That's kind of the nature of it because we are rotating, right, in kind of a circular motion. So I'm going to get kind of a bowl-looking thing, right? And it's going to look a little something like this. So there's my shape or my solid. If I took a slice of it, right, I would slice it. That was a horrible slice. I would slice it kind of around here, and you notice I'm just going to get discs, right, of varying area, right, and width. So I have to think about this disc, and I want to find, right, I want to find the area of this disc right here. So I need to know, now pretend this line should go straight through the middle of it, but I need to know this distance right here. And if you notice, if I'm stacking these discs, that's one thing to think about is, where am I stacking these discs? I'm stacking them from 0 to 8, and notice I'm stacking them vertically, so that's why I'm going to be integrating with respect to y. So what is this distance right here? Well, I know that this point right here lies on the graph y equals x cubed, but because I'm integrating with respect to y, I need to solve for x because I want to be putting in my y values, and then that x right there, so I put in a y value and it spits out a horizontal distance, right? So that should make sense that that's why I want my x by itself. So we're ready to go then. My volume then, where can I add up discs? Where do I have them? I have them from 0 to 8, right? 0 to 8. And then the area of a disc is pi r squared. So what is my r? Well, that's y to the 1/3. I know I'm going to be using the power rule, so I might as well write this as y to the 1/3, quantity squared. So let's simplify this a little bit. Don't forget, with exponents, you multiply when you raise an exponent to an exponent. So that's y to the 2/3. Take the antiderivative. If I add 1 to that, I get 5/3, I hope. And so divide by it, I get 3/5. Man, you got to watch me doing arithmetic all by myself. That can sometimes be really bad. But if you put 8 into 5/3, you know, you get a number, and I think we get about 96 pi over 5, or 96/5 pi. And you'll see a lot of my, like on the fun sheet and stuff, a lot of my solutions, I just leave it as, sorry, this is bothering me. I just leave it as a multiple of pi. You're welcome to multiply that out and give me an approximate answer. All right, let's talk about washers. So I would like to do another example, but dealing with washers. So washers are going to happen when we take kind of two functions and we look at the area between those two functions, and it gives us kind of a gap. So the example I'm going to do, again, I'm being a little lazy here, so find the region enclosed by the curves, blah, blah, blah. So we want to be bounded by, so two more examples. And actually, it's kind of one more example because I'm just going to do the same example, but for two different things. Bounded by y equals x and y equals x squared. And I want to rotate this about the x-axis. So right away, you know you are going to be integrating with respect to x. Because I am rotating about the x-axis, I know I'm going to be integrating with respect to x. All right, so first we need to find kind of the area or where these guys meet up. So I'm going to set these equal to each other. This will remind you of, you know, the last section when we found area in between curves. So I'm going to factor an x out. Remember, don't just divide each side by x here, because the minute you do that, you're saying that x cannot be 0, and we see actually that x can be 0, and x equals 0 is a place where they are going to meet up, right? So you have to be really careful about that when you're solving equations and you're dividing by a variable. The minute you divide by that variable, you're saying that that number can't be 0, because we can't divide by 0. Bad things happen when we divide by 0. All right. So we see we meet at 0 and 1, so I'm going to kind of overemphasize this a little bit. So at 1, 1, and then I know this is pretty easy, right? I know that y equals x is a line that looks like that, and then I know that y equals x squared is a parabola. Okay, and I'm going to rotate this about the x-axis. So I know when I rotate this, right, I'm going to, that point 1, 1 is going to come down here. And I'm going to get this kind of cool looking flower thing, right? That looks, pretend that's not perfect. It should be symmetric. And now when we take a slice of this, so I'm going to slice it perpendicular to the x-axis, and we see this idea of what they talked about was a washer. So if I take a slice of this, right, it's going to give me kind of a circle on the outside, and then I'm going to get this circle on the inside also, and I'm going to get this washer looking thing. So a lot of times I like to just kind of draw, oh, that looks cool, the washer. That's not a great washer, but I like to kind of draw the washer, and I like to figure out what I have going on. So let's look at what my outside radius is going to be. So my outside radius is going to correspond to that line right there. So it looks to me like this outside radius is going to be x, because that's the line. And then my inside radius, which is this y right here, this y right here, that's going to be x squared, right? So if I want the area of this washer, basically what we do is we take the area of the outside washer, which would be pi x squared, minus the area of the inside washer, which would be pi times x squared, right? And then we factor that pi out. So that's where that formula came from that you saw in your book, is just basically taking the area of the outside minus the area of the inside, and that's going to give us the area of that washer right there. Pretty, I don't know if it's simple. I don't like to say it's simple, but I mean, it kind of makes sense, right? And again, I'm slicing here. So where can I take these washers from? I can take them from 0 to 1. Okay, so I can take them from 0 to 1, and then I'm just going to integrate this right here. I'm basically adding up all of those areas of the washer between 0 and 1. So we get pi, remember that's just a constant that just hangs out, 1/3 x cubed minus 1/5 x to the 5th, all from, 0 to 1. If I put in the 1, the 0 goes away, I get 1/3 minus 1/5, right, which I believe is 2 pi over 15. Should be positive, right? We're dealing with volumes, so it would only make sense that my volume should be positive. Same thing with your areas. I was doing your guys' fun sheet solutions a little bit ago, and I got a negative area and knew something went wrong. So I checked my answers, found I had made as it always is, an arithmetic mistake. All right, so let's do, I want to do the same one, but I want to do one that's a little bit harder. So this is the last example. Wow, this might be my shortest video for you guys yet, but I want to do the same thing. I want to still be bounded by y equals x and y equals x squared. Okay, but now instead of revolving this guy or rotating it about an axis, like an x or y axis, I want to rotate about a line. Rotated about the line. So this is going to be a little interesting. So maybe I won't get done early because this might take us a few minutes to kind of figure out. So now I actually want to rotate this guy about the line x equals -1. Okay, so we know what this is going to look like. Now notice, I know I'm going to rotate about the line x equals -1. So I need to give myself a little bit of room here to see that. So I am still going to look between 0 and 1, right? I know that this is the shape of my solid. No, don't do that. I'm actually going to try and... Okay, so there's... Sorry, hold on. I gotta undo that really quick. There we go. There's the shape of my solid, kind of, sort of. And I know I'm gonna go about -1. So here's the thing when we do that, what's actually gonna happen, so this is gonna be my line. So the line y equals x, right, looks like this, and we're gonna rotate about this line right here. So I am going to be integrating with respect to y. I'm gonna need to move this over a little bit. Why am I going to be integrating with respect to y? Because I am rotating about an axis that is parallel to the y-axis. If I had said I was rotating about like y equals -1, then it'd be integrating with respect to x. So whatever axis is parallel to the axis of rotation is what you're going to integrate with respect to. Again, this is going to change in 6.4, so just take that a little bit with a grain of salt. So, so if I take this guy and rotate, this is my new axis, right? This right here doesn't have any function in it, so it's going to be mimicked over here with no function values in that, right? So this space on the other side of x equals 1 is also not going to have a function in it. So what am I going to get? I'm going to start right here, and then I'm basically going to get the same function, right? But just reflected about that line right there. That looks really weird, but it's going to be this kind of cool looking thing where there's nothing really in the middle of it, right? But again, like a kind of a tulip looking thing, but no middle. So it's just kind of a bowl looking thing with slanted insides, but no middle. So let's see what would happen. Again, I rotated about an axis that's parallel to the y-axis. So I'm going to be stacking these washers up. I'm going to be stacking these washers up, right? Oh, sorry about that. I'm trying to make this look. I'm going to be stacking these washers up horizontally, and I'm not very happy with that picture. Sorry. Try drawing these. A lot of times I'll just sit and practice this in my office. Let me try that again. So I'm going to take some y value. It doesn't kind of... Apparently I have to be quiet when I do this. Any general y value, right? And I want to think about what is going to happen to this. And so this is the washer that I'm going to get, right? And it kind of goes behind, and you can kind of see how those are going to stack up along this surface and give us our volume. So now that we've kind of drawn a horrible picture of it, let's figure out how to find the volume of this. So again, I'm going to kind of draw a representative washer, right? So I can kind of figure out what's going on here, especially with this -1 stuff. Like there's some weird stuff going on here, right? So let's figure out, I need to figure out the distance of my big washer. So if I'm at some y value, let's look at this distance right here of my big washer. Well, you guys, you know that this distance right here is -1, right? And then what is this distance going to be? Well, this is going to be whatever x is when I'm on this line y equals x squared. So if I solve that, then x is going to be the square root of y. So what is the large radius going to be? It's going to be, sorry, it's not -1 because it's a distance. It's the absolute value of -1, which is just 1, and then plus the square root of y. Or you could think of taking the square root of y minus a -1, right? The distance between those 2 points. And if I subtract a -1, then I get 1. What about the inside of this washer? So the inside of this washer is going to be this right here, this green distance. Again, same idea. I know this distance here is 1, right? And then here I know that this distance here is y equals x, or in our case, x equals y. So what is the distance of the inside washer going to be? That is going to be 1 plus y. I hope that makes sense. I know that picture isn't super perfect, but if you can kind of draw a picture of it and then just kind of break it up into little sections, right? Figure out what that big radius is, figure out what the small radius is, and then move on from there. And if you look, I have an example of one similar to this on the fun sheet, and of course in your homework, right? So what is my volume? All right, so let's see, where can I stack these beautiful washers? Remember, we're going in the y direction. Well, I can have one at 0 and then all the way up to 1. So I'm going to go from 0 to 1, pi times the outer radius squared minus the inner radius squared. Oh my goodness, this is going to be fun. dy. I'm going to FOIL this out. That's the only thing I can do, you guys. I can't really do substitution because I don't have its derivative sitting there. If you don't know how I'm doing this, we should, schedule an appointment to get together or, hang out. So let's simplify this. I really, really encourage simplifying your integral before you actually take the integral. It just is gonna make it just a little easier to work with. So I have -y, my 1's canceled, minus y squared dy. This is looking pretty good. And now, of course, the easy part, right, is to take the antiderivative. So I believe that's 2/3 y to the 3/2 minus 1/2 y squared minus 1/3 y cubed, all evaluated from 0 to 1. I will not bore you by doing that all for you. That's not super fun, but it actually comes out pretty nice. It comes out to pi over 2. I don't know if this is the shortest video, but it's not too bad. 22 minutes, not too bad. I hope that makes sense. I hope my picture made sense. I'm sorry I'm not the best 3D drawer. Look in your book. Your book has some great pictures of it. You could even, Google just some videos of these they're called solids of revolution. That's something you can Google. And then, of course, if you want to get together with me, we could get together and do like a web meeting, and I can show you some animation in that web meeting if you want to. All right, you guys, have fun.